Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. Here in this video we are going to conclude our chapter Avalanche Transit Time Devices, and we'll be starting by the next lecture a new chapter. So here, as for Avalanche Transit Time Devices, we are covered with impaired diode, trapped diode, buried diode, parametric devices and parametric amplifiers. Here we solve a last practice problem onto parametric amplifier. A problem statement is given to us. A negative resistance parametric amplifier has the following parameters. The parameters are denoted by, here we have signal frequency f suffix s is equal to 2 GHz, f suffix p is equal to 12 GHz, f suffix I is equal to 10 GHz, f suffix d is equal to 5 GHz. The resistances are r suffix I 1 kilo ohm. The next resistance is r suffix g, again 1 kilo ohm. Here we have RT suffix S 1 kilo ohm, and the last resistance that it is R suffix TI is equal to 1 kilo ohm. Along with we are provided certain parameters represented as R is equal to 0.35, R into Q is equal to 10, R suffix D is equal to 300 degree Kelvin, C is equal to 0.01 picofarads here. We are asked to calculate equivalent noise resistance, gain, noise figure and bandwidth. Now to read out this problem statement, whatever we have earlier denoted as gamma into Q in this problem has been given as R into Q. So accordingly the same is to be substituted into the respective formulae here. Also the diode temperature here is represented like this. So either you can use T suffix D also. The unit is in terms of degree kelvins here. Now let us have computations for the part A in the equivalent noise resistance. Now for part A, the equivalent noise resistance can be denoted simply by capital R. So here we have R is equal to small r square divided by, here we have omega s into omega I into c square r into t suffix I. So we have all the values available to us. Now we can make substitutions. So by the next step here, we get it to the form 0.35 to be squared here in the numerator. In the denominator, we have omega, that is the angular frequencies, can be represented in terms of the frequencies by 2 pi f here. So therefore we can take 2 pi's from these two frequencies common, and here we can represent it as 4 pi square. And now rest of the two values for fs and fi can be represented as 2 into 10 into, here it becomes 10 raised to the power 18 into the next value for the capacitor, it is 0.01, it is to be squared, into here we have 10 raised to power minus 24 into 10 raised to power 3 here. So finally we obtain the answer as 1.55 into 10 raised to power 3. So as this is the resistance, it should be expressed in terms of ohms here, and absorbing the multiplicand 10 raised to power 3, we can get it to the form 1.55 kilo ohms here. So this is the required value of resistance as the part A here. Now we are completed with the answer for equivalent noise resistance. For the part B, we need to calculate the gain here. For calculation of gain, we can make the use of one ratio represented as small a is equal to R divided by RT suffix S here. So the obtained answer from part A can be used here, that it is 1.55 into 10 raised to power 3 divided by 1 kilo ohm, that is 1 into 10 raised to power 3 representing the kilo here. So this gives us again the value 1.55. Now the formulation for the gain can be represented 4 into Fi divided by Fs in multiplication to, here we have Rg into Ri divided by Rt suffix s into Rt suffix I in multiplication to A divided by 1 minus A squared here. So this gives us 4 into 5 into 10 raised to the power 6 into 1.55 divided by, it becomes 10 raised to the power 6 in the bracket 1 minus 1.55, the bracket is squared. The simplified value obtained by simple multiplication and the division gives us 102.88 here. Now getting it converted to the decibels form, we obtain the answer of the gain to be equal to 20.1 decibels here. So this is the value of required gain for the parametric amplifier under consideration. Now we are covered with the answer for part B. Now we require the computation of noise figure. Now for part C, the noise figure can be represented as F expressed as 1 plus, here regularly we denote twice the device temperature T suffix D divided by T suffix 0 in multiplication to, here we have instead of gamma can be represented as R also. So R into Q added with 1 upon R into Q, bracket is squared here. So substituting all the values that are available, we get the next step as 1 added with 2 into 300 divided by 300, in the bracket we have 1 upon 10 added with 1 upon 10 square here. So therefore, getting the value of F computed, we obtain 1.22, so which can be converted into the decibels, and the decibels answer is 0.86 decibels. So this is the required value of F here. Now after the calculation of noise figure, we want bandwidth to be calculated in the part D here. Now the calculation of bandwidth can be given by, here we have bandwidth represented as BW and computed as R divided by 2 square root of, here we can represent the ratio of FD to that of Fs for the gain perspective here. So therefore substitution of the values gives us 0.35 divided by 2 square root of, here we make the numerator under the square root to be 5 and the denominator as 2 into 10 raised to the power 9 into 102.48 obtained. So this gives us the value of the bandwidth. The bandwidth is obtained as 0.039 here. The bandwidth value is outlined here. So this completes problem number 3 based on to the parametric amplifier. By the next lecture, we shall be starting with the new chapter in microwave engineering. The chapter is titled Microwave Transistors and Tunnel Diode. The very first topic from this chapter we shall be addressing, that is a microwave bipolar transistor. I hope you are enjoying the microwave engineering subject, and for more information and knowledge of this subject, you can subscribe to Ekeeda channel. Thank you.